So in this video we're going to be looking at alkenes, their shape, structure and the formation of a pi bond as well. Now alkenes have a general formula of CnH2n, and that's going to be the same as our cycloalkanes, where we can actually end up forming isomers, functional group isomers between the two, where I can take something like, let's say, butanene, and butanene can form a functional group isomer with something like cyclobutane. We've got the same molecular formula, but we've got different structural formulae. Now if we were to look at these, both of these have a formula of C4, and then it's going to be H8 itself. They fit the general formula of CnH2n. Now the only difference is when we look at an alkene, we've got, yes, an unsaturated hydrocarbon. It's going to be very similar to an alkane in terms of the carbon-carbon and carbon-hydrogen bonds, but of course it's going to have a carbon-carbon double bond in there as a functional group. That's how it's going to be different. Now of course that makes it more reactive, where our alkenes can undergo addition reactions, where we can end up with a mechanism of electrophilic addition, because we've got that weak pi bond in there. That weak pi bond is what makes the actual alkene reactive, because when I look at a carbon-carbon double bond, one of these is going to be a sigma bond, which is what we need to be aware of, and one of them is going to be a pi bond. Alkanes, we know they're going to be unreactive because they contain strong sigma bonds, but alkenes, they also contain that pi bond in there, where we can add a molecule on there as well. We need to know that pi bonds, they're going to be weaker than sigma bonds overall. What about if we were to look at the shape? Well, around the carbon atoms that are going to be saturated, where I end up with, let's say, this one over here, we've got our bond angle that's going to be 109.5, and that's going to be a tetrahedral shape. Of course, we know we've got 4 bonded pairs, 0 lone pairs around that carbon atom over here, and so we know the shape is going to be tetrahedral. All electron pairs repel and whatnot like that. Now if I were to look at the carbon-carbon double bond though, right, although we've got 4 bonded pairs, 0 lone pairs, we've actually got 3 bonding regions. I've got 1, 2 and 3 around this carbon atom over here. So I know I end up with 120 degrees because we just treat it like 3 bonded pairs, and that's going to be our bond angle. The shape itself is going to be trigonal and then planar itself. So moving on then, what is an actual sigma bond and a pi bond? We've already visited sigma bonds when we were dealing with alkanes, but basically if you were to look at a covalent bond, where of course you end up with a shared pair of electrons, and let's say it's going to be between 2 carbon atoms or carbon and a hydrogen, you can end up with a sigma bond where you end up with the end-on-end overlap, and it's going to be directly between your bonded atoms itself. If you were to look at a pi bond is going to be different because you've actually got the sideways overlap of p orbitals to give a pi bond that's going to be above and below the plane. Now let's say if I were to look at this molecule over here, which is going to be a general alkene, we can show the formation of an actual pi bond by drawing a pi bonding diagram, and what I'm going to have over here is of course my p orbital, which of course is going to be one lobe there, another lobe there, there's one p orbital, and then over here I've got another p orbital, I've got another lobe here, and you can see over here I've got 2 p orbitals. Now what's going to happen is that these p orbitals, how they actually bond together and overlap together is that they both expand. So this one over here is going to expand, this one over here is going to expand, and they end up overlapping, and what we actually end up forming is a shared pair of electrons. We form the sideways overlap of our p orbitals to give a pi bond above and below the actual plane itself. We can actually draw this out like this, where I end up with, of course, a pi bond, and it's going to be our electrons, 2 electrons whizzing, of course, above and below the actual sigma bond itself. Now of course with any good diagram, because this is an exam question, you need some labels on there, and of course over here I've got my p orbital, which is what I'm going to label. I've got my sigma bond down below over here as well, and then I've also got my pi bond, which is going to be of course both of these two over here. That's going to be 1 pi bond. And then above the arrow I like to put sideways overlap, so I get the marks in the exam as well. Yeah, so that's how we can form a pi bond. Now if I were to look at an example of ethane and ethene, right, you need to be able to count the number of sigma bonds and the number of pi bonds in these structures. So if you look at ethane, right, every single bond that you see, we normally say that a rule is that that's going to be a sigma bond. So in this case I've got 1, 2, 3, 4, 5, 6, and then 7 single bonds. So I know of course we've got 7 sigma bonds in total. If I were to look at something like ethene, I've got 1, 2, 3, 4 single bonds, and in this case, in this double bond, one of these is going to be a sigma bond. So in total I've got 5 sigma bonds in this molecule of ethene. But the second bond within this, of course, that's going to be our pi bond, and so we say we've got 1 pi bond as well, and there's that one done too. So moving on then, I want you to have a go at the following task. I want you to determine the number of sigma bonds and pi bonds in the following molecules. So looking at this question then, I've got here, of course, a molecule of 2-methyl-propanone. And of course, what I like to do is draw out the displayed formula just so I don't make any silly mistakes, because really that's what the examiner is checking. Are you systematic about these things? And of course, are you getting the right answer? Because it's a pretty low level exam question, but you can make quite a lot of silly mistakes. So over here, of course, I've drawn out the displayed formula, making sure every carbon atom has 4 bonds, no more or no less. And that seems to be fine in this case. And then I'm going to count my number of pi bonds first because that seems easier. So yeah, in terms of this then, I've got 1 pi bond which is going to be within here, and then of course I've got 1 sigma bond which I need to be aware of. So in that case, my pi bond's pretty much done. What about the number of sigma bonds? Well, I've got 1 in the double bond there, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sigma bonds altogether as well. So in that case, my answer for that one is 1 and then 11. Now looking at B, right, we've got here an alkene. It's going to be pentane 1, 3 diene. So in this case, right, if I were to, let's say, go through in a quicker method, I can actually count out how many bonds that I've got missing, because they're going to be, of course, to each hydrogen. So I've got over here, right, my missing hydrogens added on, and then now I'm going to count the number of pi bonds that I've got. So that's going to be easier. I've got 2 pi bonds over here, right, 1 in this double bond over here, and I've got 1 in this double bond as well. And don't forget, you've actually got a sigma bond in there as well. A lot of people tend to forget this. So in this case, I end up with 2 pi bonds. That's that done. And then what about sigma bonds? Well, I've got 1, 2, and then there's 3 there. Then there's 4, 5, 6, 7 there. 8, 9, 10, 11, 12 sigma bonds in total. So my answer for this one is going to be 12, and then it's going to be sigma bonds itself. And there's that structure done there as well.